talk about chemical equations. Chemical equations are how chemists express reactions. Okay, they're expressions for reactions where we use the elemental symbol and subscripts and coefficients. Okay, a very simple chemical reaction might look something like this. If we had hydrogen gas and we add to it oxygen gas, what do you think we could form? Beautiful. We can form water that way. Okay? We can also, this is called the skeleton equation. Okay? A skeleton equation is not a balanced equation. What do I mean by that? We have symbols, we have subscripts. Can you tell me how many hydrogens we have on the left side of our equation? We have 2. How many do we have on the right side of our equation? 2. There's the same number of hydrogens on this side as that side. What about oxygen? How many do we have here? We have 2. Did an oxygen disappear? Did we destroy it? No. This equation isn't balanced, okay? It's called the skeleton equation. Let me back up real quick and ask you this. What do we call these over here on the left side of our equation? Or the reactants, thank you. These are my reactants. Okay, and they react to produce what? What do we call this over here? A product. Product. Perfect. Can you tell me the relationship, Bryce, between the mass of my reactants and the mass of my products in any chemical reaction? They would be the same. Let's put it as equals, right? This is the conservation of mass. We've talked about it from the start. The mass of your the mass of your reactants will always equal the mass of your products. Okay? You got that? You good? Okay. Now, do you see this equal sign right here? You see that, Bryce? Let's have a look at this side of the equation and this side of the equation. What's similar here in the middle? I got an equal sign here. Here I've got an arrow. Is that arrow kind of like an equal sign in my equation? Yeah, it kind of is. Okay, so what that equal sign means is, when we're writing a chemical equation, have you ever heard this sign? It calls this yields or produces, okay? Produces. These reactants, when they react together, produce this product. Hydrogen and oxygen react to produce water, okay? I can write those words, okay? A lot of times chemists are just talking to each other. They say things like this. Iron 3 oxide. Do you remember what that was? Iron 3 oxide? We could break that apart. Actually, let me go the other way. Be simpler. Iron plus oxygen. I'm going to write it with words. I said I would. Iron plus oxygen react to form or produce or yield iron. I'm writing the symbols again, sorry. Iron 3 oxide. This is a word equation. Okay? I'm just describing this, okay? Check this out. Can you tell me, what do you think the state of iron is? It is a solid or liquid or gas? It's a solid. What do you think the state of oxygen is? Solid, liquid, or gas? Gas. Do you see these little symbols I'm putting right here? This is a parentheses with an S for solid. This is a parentheses for gas. What if I had a liquid? Would I put my parentheses? I know, for liquid. Good. And iron oxide, that's rust. What do you think the state of matter of that is? Releasing rust. It's a solid. This is a word reaction, okay? A word equation, excuse me. I'm explaining in words a chemical equation. Solid iron plus gaseous oxygen reacts to produce iron 3 oxide, solid iron 3 oxide, okay? It's a word equation. I can also use symbols to express the same thing, and chemists, when they're writing equations, do express these as symbols. What's the symbol for iron? Fe, and it's a solid. What's the symbol for oxygen gas? Is it O or is it O2? It's always O2. We always find oxygen as O2. Those react to form iron 2, oxygen 3. Okay? And that is a solid. This is a chemical equation. We've taken these words or these concepts, we've used symbols and subscripts and arrows to turn this into a chemical equation. What is the mass of the reactants in relation to the mass of the products? The same. Conservation of mass says if I have 5 grams of iron and say 5 grams of oxygen, it wouldn't work that way. But how many grams would I end up over here with my rest? 10 grams, okay? It would have to balance. So that's the general concept we're going to discuss over the next couple of days. This is your introduction to chemical equations right here. How do you describe what happens in a chemical reactions? The reactions are written on what side? The left side. And the products are written on the right side. An arrow separates them. We draw like this. That arrow kind of means equal, doesn't it? You read the arrow as yields, gives, or reacts to produce. Okay? When you're reading the equation, you say iron plus oxygen react to produce or yield rust or iron oxide, iron 3 oxide. And it looks like this. Reactants equals products or yield products. Next, how would you describe the rusting? We already did. Iron reacts with oxygen to produce iron 3 oxide. Okay? And that's what I just showed you. It's quicker to identify the reactants and products by means of a word equation. So you say iron plus oxygen react to form iron 3 oxide, but that's not really something that chemists can use. So we use, that's our word equations. In a word equation, the names of the reactants on the left side separated by plus signs. What do the plus signs mean? What do those plus signs mean? No, the plus signs mean that they're combining, okay? That they're reacting. That's what the plus means. The arrow means yields, okay? No plus sign is needed in the product side of the equation because there's only one product, okay? If we produce 2 products, we would use a plus sign between those 2 products. Moving on. Anybody ever put hydrogen peroxide on a cut or a scrape and it fizzes? This is the reaction that's happening there. It looks like this. Hydrogen peroxide breaks apart or decomposes to form water and oxygen gas. Okay, there's your word equation right here. Hydrogen peroxide, that's the stuff in the bottom of your cut, makes water and oxygen. Okay, that's my word equation. Can anybody guess what the chemical equation would be if we were writing with names and formulas instead of names? How do we write hydrogen peroxide? Do you remember? It's one hydrogen per oxygen, but it's H2O2. It reacts to form water plus oxygen. That's a chemical formula, okay? This is a word formula, that's a chemical formula. Let's move on. Here's another one. You turn on your stove and out comes natural gas. That's methane plus oxygen yields carbon dioxide plus water, and that's what's going on right here, okay? It also yields, what else does it yield? Why do we actually burn methane on our stoves? To create what? Heat, right? So you could also say plus heat, okay? That's the full reaction. We're actually creating heat by doing this combustion reaction, okay? We'll get to the chemical reaction later, and do we have any more? Here we go. Chemical equations, okay? Now we're moving away from the word equations and we're writing more like a chemist. A chemical equation is a representation of a chemical reaction. It's how we represent a chemical reaction with symbols and numbers, okay? Reactants are on the left, products are on the right. This is that one that we did together for rusting. You've got iron reacts with oxygen to produce rust, or iron 3 oxide. Okay, so that is how we move from word equations to chemical equations. Next, you asked about balancing equation. Right now what we're doing is we're writing skeleton equations, okay? Skeleton equations, we don't worry about balancing the mass yet. The first thing we do to write a skeleton equation is replace the words with the symbols. That's all we're doing, okay? So a skeleton equation, as you can see, as Brett brought up, how many ions do we have in the product? We have 2. How many do we have in the reactants? 1. We are not destroying mass, okay? We will have to balance this equation later, but right now all we want to do is write a skeleton equation that doesn't balance. All it has is the reactants and the products. See, we've got 2 oxygens here, and we have 3 here. They don't balance. That's okay. We actually have the correct chemical formulas for the reactants and the products, and that's where we start. Next. This is the only time I'll talk about it I'll talk about it in detail later. This is the only time I'll talk about it in Chapter 11, a catalyst. Does anyone remember what catalysts are called in biology? I think you've all had biology. They're called enzymes. What do enzymes help us do? They help chemical reactions, right? Do the enzymes get used up in the chemical reaction? They get used over and over, right? They get recycled. That is called a catalyst. In chemistry, we call that a catalyst. A catalyst is a substance that speeds up the reaction, but is not used in the reaction. And for that peroxide reaction that we talked about, here is a catalyst. We write it right there. Okay? I think that's manganese oxide. Okay? We'll get to that in a second. And here we go. And that's the second. Here's a table that's from your book of the symbols that we use and what they mean when we're writing reactions. Okay? We already talked about the plus sign. That separates 2 reactants or 2 products. What if you have 3 products? You'll need another plus sign, right? What if you have 4 reactants? You'll need a plus sign between each one. Okay? So that's what the plus sign is. The arrow is the same as it's kind of the equal sign of our chemical equation, and it means yields or produces, okay? And it separates the reactants on one side from the products on the other. Sometimes reactions go in both directions. You form the product, and the product can break down and go back to the reactants. And then we would use this symbol right here, arrows in both directions. We won't be using that a lot right now. In fact, I don't think we'll use it any. We might use it later. We talked about solid, liquid, and gas. Okay, you're going to describe the state of matter. This one right here, aqueous. I already had that question. An aqueous solution, if you put, for instance, salt, like table salt, NaCl, and water, it forms an aqueous solution. It's NaCl with a parentheses aqueous behind it. That means it's in water. A couple other things. If we add heat to make the reaction happen, and we do that for many reactions, you write a triangle, or you write heat right over the arrow, okay? Triangle, or heat. And last thing, if you have a catalyst, you write its name over the arrow, okay? That catalyst right there is platinum. PT stands for platinum. Does anyone know that they have platinum catalyst in a device that we use most every day? Not catalyst. No?
Microwave.
Has anyone ever heard of a catalytic converter on their car? It has platinum in it, and it creates less harmful combustion reactions than if you just let the gas go right out your tailpipe. Okay? It actually completes the combustion reaction. Those are the symbols that are from your book. I'm going to touch on balancing equations so that you can do that first part of your worksheet. Okay? A balanced equation has the same number of atoms of each element on both sides of the equal sign. It's just like algebra, okay? The 2 sides have to equal. Do we create mass? Do we destroy mass? No. Do we destroy atoms ever? So if they appear in the reactants, if you have 4 of an atom, how many of those atoms will you need on the product side? 4, okay? So we don't destroy atoms of an element. In any chemical reaction, I'm going to go back to, mass is conserved. The atoms themselves are neither created nor destroyed. They are merely rearranged, okay? So to balance an equation, what does it mean? We use coefficients in front of the molecules to balance equations. We do not change the subscripts. If you had this compound right here, water, then you could have 2 waters, or you could have three waters, or you could have 10 waters on the side of an equation, but you can't, so you can change this coefficient. You cannot change the subscripts. You can't change that. You can't change this invisible one. It must stay water on its side of the equation. When it moves to the other side of the equation, you may have you might have hydrogen 2 and oxygen 2, but you cannot change the subscripts on a molecule. Or you're changing what type of molecule it is, okay? Here's a very simple balanced equation. Ready, Joel? Very simple. We have 1 carbon atom. It reacts with 2 oxygen atoms in O2, and it forms carbon dioxide. 1 carbon, 2 oxygens. The formula there, if you can see it, it's written right here, CO2. Does this balance? How many C's do I have on this side of the equation? 1. On this side of the equation, 1. How many oxygens do I have? 2, and I have 2 oxygens on that side. So I have the same number of atoms on both sides of this equation. You don't even have to change the coefficients. Water's a little different, Maria. If I have hydrogen gas, do you remember when I talked about this word? Diatomic. Remember that word? Here are your diatomic gases, right here. Hydrogen in nature always forms H2. Always. You never see it just as an H, okay? You're always going to see it in nature. When it's by itself, it's got a partner, okay? Nitrogen in the atmosphere is always N2. It forms a diatomic molecule. Oxygen, again, always a diatomic molecule. And all of the halogens that we're going to be using. What are the halogens? Group 17, right here. These guys, we always see F2, Cl2, bromine 2, iodine 2. When they're by themselves. If they're in a compound, you may only see 1. But when they're by themselves, you're going to see 2 of them. So remember this little L right here, an upside down L. Do you see it? Nitrogen, oxygen, and then all the halogens. What else? Hydrogen, okay? Those are the ones you have to remember. They form diatomic molecules, okay? So, if we have hydrogen, we're going to see it as H2. Do you see that right there? Oops. And if we have oxygen, it's O2. Those 2 things react to form what? Water. H2O. Let me ask you though, how many oxygens do I have on the left side of my reactants? I have 2 oxygens on my reactants. How many do I have in my products? Only 1. Did we destroy that oxygen atom? No. We didn't destroy it. What we actually did is, we would have actually needed to create 2 water molecules. See 2 oxygens here, we would create 2 water molecules, but what am I missing? Now I have how many hydrogen atoms on this side? 1, 2, 3, 4. What do I need to do over here? I need 2 more hydrogen atoms. That looks like an 8, doesn't it? It's supposed to look like that. Okay? So we need 2 more hydrogen atoms. I just balanced this equation. How many hydrogen atoms do I have over here? 4. How many do I have over here? 4. How many oxygen atoms in my products? 2. And I have 2 oxygen atoms in my reactants. So this equation balances. If I have 2 hydrogen molecules, that's 4 atoms, and 1 oxygen molecule, which is 2 oxygen molecules, I can create 2 waters. And here's what it would look like if it's balanced. This is the intermediate step that I did. They said, oh no, we're going to make 2. See that 2 in front of that H2O? See that? coefficient right there. We're going to make 2 water molecules. And so now we need 2 hydrogen molecules. What does the equation look like when you just write it without these big bubbles? 2 H2 gases plus oxygen gas reacts to form, and I'm going to write it down here, 2 H2Os, and they are liquid. Well, you see that? I just balanced an equation. Here's some rules for balancing an equation, but really you just have to practice. The first step in balancing an equation is write the skeleton equation. When I say skeleton equation, what do I mean? Words or just symbols? Just symbols. For the water reaction, you would write this. Hydrogen gas plus oxygen gas, that's H2 and O2, react to form water. Is this balanced? This is not a balanced equation. I write the skeleton equation first, and then I start looking at my hydrogens. Are they balanced? If I told you that we're going to take hydrogen, this is a word equation, hydrogen gas plus oxygen gas, and they react to form liquid water. That's my word equation. The first step when you're told this is to substitute chemical formulas. In a skeleton equation that's not balanced, we get hydrogen gas, and we get oxygen gas. You see that? That's how diatomic molecules appear in nature, and those react to form water in the liquid form. That's a skeleton equation. That's your first step, Joel. Next, we have to balance this equation by changing only the coefficients. Right now, the coefficients are only 1, so we don't actually show them. How many hydrogens do we have on the products, on the reactant side? We have 2. And we have 2 hydrogens on the product side. Are they in balance? Yes. What about oxygens? I have 2 oxygens on the reactant side and only 1 oxygen here. How can I put those oxygens in balance? By changing a coefficient. Which coefficient? How about this one right here? What if I put a 2 here? How many oxygens do I have over here now? 2. How many oxygens do I have here now? Still 2, right? So this is an invisible 1 in front of that oxygen. But what happened when I put the 2 over here? Now I've got how many hydrogens? 4. So what do I need to do to the coefficient on hydrogens? I need to be a 2. This is a balanced equation, which is what we're going to practice for the rest of the week, and I am